Let's look at algebraically what happens when you take a limit as x approaches either positive infinity or negative infinity. In earlier videos, I've already kind of talked about graphically what this looks like, but I'll mention a little bit of that here too. So let's look at limits at infinity. And in particular, for this video, let's focus on ratios. Some techniques you can use algebraically with ratios. Okay, so we'll kind of jump right into an example because we can quickly see the issue when you have a limit of a rational function as x goes to infinity. So let's consider the limit as x goes to infinity of 5x cubed plus 2x minus 4 over, let's say, 3x squared minus 7x plus 1, okay? And we want to take the limit of that as x goes to infinity. And so the immediate idea is to imagine what would happen to this ratio as x gets very large. And so hopefully what you could see is that as x goes to infinity, 5x cubed goes to infinity, 2x goes to infinity, 3x squared goes to infinity, negative 7x goes to negative infinity, right? Because you got a negative 7 times a really big positive number. And then the minus 4 and the plus 1 are negligible when you're talking about massive values that are going to infinity. So what we end up getting is, if you imagine what this looks like, you end up getting what's called an indeterminate form. And this video is not really about indeterminate forms, but it's a pretty heavy topic in calculus later on. So might as well mention the term here, an indeterminate form. And let me show you what that means. It means that infinity on the top, as x goes to infinity, the top goes to infinity plus infinity minus 4. Well, the top is going to infinity then. And the bottom, as x goes to infinity, is going to infinity minus infinity. Now hold on a second. Infinity minus infinity. Don't mistake that for something like 5 minus 5. 5 and 5 have equal values. Therefore, we can subtract and get 0. Infinity minus infinity is what we call an indeterminate form in itself, typically, because some infinities are bigger than others. So we have to be really careful there about applying the rules of our real number system to these infinite quantities. But in this case, here we're squaring infinity, and here we're not. So this infinity is infinitely bigger than this infinity, if that makes sense. So when I subtract them, this guy, this 3x squared, really does dominate the negative 7x. So this turns into an infinity minus a smaller infinity. So we still have infinity plus 1. And so it appears that as x grows without bound, the numerator grows without bound and the denominator grows without bound. And so what we see is we get something like infinity over infinity. Now again, we just talked about some infinities are bigger than others. And so this does not necessarily equal 1. It can in some cases. In some cases, it could be infinity if the top infinity is infinite times bigger than the bottom infinity. In some cases, it could be 0 if the bottom infinity is infinite times as big as the top infinity. It's indeterminate in that form. So we have to do some technique to see if we can learn more about this limit. So a great technique for this is to try to eliminate the indeterminacy of this ratio. And one way we can do that is if we could somehow turn the denominator into a constant. So let's take a detour for a moment, and we'll come back to this. So a slight detour. Let's look at some more basic limits as x goes to infinity, and then we'll see how they can help us solve this problem. What do we get if we take the limit as x goes to infinity of 1 over x? Well, we have a constant on top divided by something that's getting infinitely big. That's clearly going to get infinitely small. That limit's going to be 0. And in fact, it's true whether this infinity is positive or negative infinity. Let me kind of separate this. Because even if we take 1 divided by a really big negative number, well, we're still going to get 0 ultimately. It's going to approach 0 from the negative side, but ultimately it's going to go to 0. Okay? So that's key. And you could probably imagine there's nothing special about 1 other than the fact that it's a constant. So if we take the limit as x goes to positive or negative infinity of any constant over x really to any power, let's call it r for rational, has to be a rational power. So whole numbers, of course, like x to the first squared cubed are rational, but you could also have some fractions here. And I won't get into all the intricacies of here because some strange things can happen if you're looking at negative values for x and you have rational exponents that have an even denominator. I said that kind of fast. You might want to rewind if you want to go investigate that on your own. I'm not going to do that here. But you can imagine that if the top number is fixed and the bottom number is going to infinity, then this ratio, this limit of this ratio is going to go to 0. Okay? It's also true if you look at something like the limit as x goes to infinity, let's forget the plus or minus now, of 1 over e to the x. Well, as x gets big, e to the x also gets big, infinitely big. So we're still taking 1 divided by a massive quantity, which is going to give us a small quantity. And this works for lots of different functions, such as 1 over the natural log of x. As x grows, the natural log also grows. So this again turns into 1 over infinity, which is 0. Now isn't that nice? This is the power of infinity when you're dealing with ratios. We want to leverage that in this example. So what we're going to do is we've reached the end of our detour. Let's come back on track. What we're going to do is we're going to take this ratio and we're going to multiply by something that's going to fix this indeterminate problem. The way we do that is we'd like to turn the bottom into a constant. We don't want to divide by 0, of course. We also don't want to divide by infinity in this case, because the top is infinity. So what we're going to do is we're going to try to turn the bottom into a constant. And so let me show you how you do that. We're taking into account that we're doing a limit, okay? So keep that in mind. So what we're going to do is we're going to multiply by something that's going to turn the highest power of x. You may want to write that down. We're going to multiply by something that's going to turn the highest power down here into a constant. So to do that, I would have to get rid of this x squared and make that a 3. I can do that by multiplying by 1 over x squared. Because if you multiply 3x squared by 1 over x squared, the x squareds cancel and you just get 3. But if I do it on the bottom, I have to do it on the top as well. Okay? So this is kind of a fun little deal. You'll see why it'll work out nicely. Again, the goal is to make a constant on the bottom. Now you may be asking, well, what about this negative 7x and the plus 1? You'll see what happens to those when we apply this limit shortly. So this turns into the limit as x goes to infinity. And on the top we have to distribute, right? Because we have to multiply the numerators, and on bottom we'll distribute also. So on top I'll take 5x cubed divided by x squared. That's just 5x. Plus 2x divided by x squared. Well, this x cancels with one of those, leaving an x on the bottom. So this turns into 2 over x. Minus, there's no x's to cancel, so I just get 4 over x squared. Multiplying by 1 over x squared is the same thing as dividing everything by x squared. Simple. On the bottom, we distribute. Divide by x squared, and we get 3. Divide by x squared, one of the x's cancels, and we get minus 7 over x. Divide by x squared, and we get plus 1 over x squared. And so now what we see, now let's try to apply the limit and see what happens. This is the cool part. This is always exciting and fun for me, even to this day. I like crossing stuff out. So as x goes to infinity, all of these ratios with a constant on top and x to a power on bottom go to 0. So a fun way to show that without rewriting a bunch is just to draw an arrow through that and say, well, that's going to go to 0 whenever x goes to infinity. And the same for this guy, and this guy, and this guy. And so what ends up happening is, you can see what we're left with on the bottom is just the 3, just the constant of 3. So ultimately, we get the limit as x approaches infinity of 5x, which is not a constant, okay? We're not worried about the numerator, but that's over 3. So what happens now? As x goes to infinity, if you imagine what this does, well, 5 times infinity, you can imagine, is infinity. And on the bottom, we just have the constant 3. See the difference between these? This is not indeterminate. If we take larger and larger and larger values and divide by 3, we're still getting larger and larger and larger values. Thus, this limit equals infinity. Okay? All right. So this is a case where this indeterminate infinity over infinity, through more inspection, actually equals infinity. So again, don't assume that infinity over infinity equals 1. All right, so we're going to move a lot faster now because that was the technique we needed to do a lot of examples. When it's cold out here, this does not want to erase, so a rag does a better job. Okay, so let's look at another example here. Let's take the limit as x goes to infinity of 4 minus the natural log of x over 3 times the natural log of x. And this is the same problem. If you were to look at this for infinitely large values of x, this guy goes to infinity and this guy goes to infinity. So on top we'd have 4 minus infinity, which is negative infinity. And on the bottom we'd have 3 times infinity, which is positive infinity. And because again, we don't know who wins the infinity battle when we're dividing, this is indeterminate, we've got to investigate further. But we use the same idea, even though we don't have polynomials. I'd like to make the bottom a constant. So what I can do here, let me erase this. What I can do here is divide the top and bottom, or multiply the top and bottom by 1 over the natural log of x. Okay? And so what we get here is the limit as x goes to infinity. And because we have the minus here, I have to distribute across it. I get 4 over the natural log of x minus the natural log of x divided by the natural log of x is 1 over 3 times the natural log of x over the natural log of x, cancels and leaves just the 3. And so now I'm going to pick up my old friend, the trusty red marker, and as x goes to infinity, the natural log of x goes to infinity. So 4 divided by that goes to 0. And so we can see that as x goes to infinity, this ratio goes to negative 1/3. So you can see the power of this. So in this case, we had negative infinity over infinity. The ratio of those actually gave us a constant, not an infinity, which is totally possible. Okay, let's do another one. Let's look at the limit as x goes to infinity of x times the square root of x plus 3x over 4x squared plus 1. So what we want to do is, you may be thrown off by this x square root of x. So let me discuss that for a minute. How about that? The square root of x is the same thing as x to the 1/2 power. And this is x to the first power. So what we see is x times the square root of x is the same thing as x to the first times x to the 1/2. In other words, we have 1.5 x's being multiplied. So that's the same thing as x to the 3/2 power. Okay? You add the exponents here when you multiply with the same base. Should remember that from basic algebra. So this is x to the 1.5 or x to the 3/2 power. So this is still all just x to a power. Okay? So we'll keep that in mind and we'll utilize as we work through the problem. But if we look at this as x goes to infinity, we have infinity times infinity plus infinity over infinity, indeterminate, right? So what we're going to do is look at the bottom. I'd like to turn the highest power here into a constant, which is this 4x squared. So I'm going to multiply the top and the bottom by 1 over x squared. And I'll distribute it on the top and the bottom. And so the result, well, let's do a little bit of work here. Let's show a little bit. I don't want to scare you off with this x times the square root of x. X times the square root of x, remember, is x to the 3/2 power. And I'm multiplying by 1 over x squared. In other words, I'm dividing by x squared. So it's just that. We can simplify it on the next step. Plus 3x over x squared. Well, now it's pretty simple to cancel an x. Yeah, we can cancel an x with one of those to give us 3 over x. On the bottom, 4x squared divided by x squared is 4. That's the reason we did this. Plus 1 divided by x squared is 1 over x squared. Okay? Now, we could certainly go further with simplifying this. If you want to simplify this, you have more x's on bottom than you do on the top. In fact, if you were to cancel those, you would cancel 1.5 x's from here, getting rid of all the x's and just leaving behind a constant of 1. And you'd cancel 1.5 of the x's down here, and that would leave x to the 1/2 power. So this turns into 1 over x to the 1/2. Let's go ahead and do that. It will not hurt a bit to do that. So this turns into 1 over x to the 1/2 when you cancel, plus 3 over x over 4 plus 1 over x squared. And now we can utilize the power of the infinities on these ratios. 1 divided by infinity is 0. This is 0. This is 0. And so what we're left with now is on top, which is a little different than the others. We're left with 0 on the top, and we're left with 4 on the bottom. And 0 divided by 4 is just 0. Okay? So sometimes infinity over infinity equals 0. And this is a good example of that. I brought this example in to show you how to deal with square roots and turning them back into powers. All right, let's do one final example with this and sort of throw in a bit of graphing with it. or graphing concepts anyway. Okay, so let's look at, we're going to do two limits with this function. Let's say we've got, let's name it. So suppose f of x equals, and we'll do a rational function again, and let's say on top we have x squared minus 4x plus 3, and on bottom we have 2x squared minus 7x minus 4, and we'll do some stuff with that function, okay? So the first thing is, well, let's do the obvious thing. Let's do what we've been doing, and let's consider the limit as x approaches infinity of f of x, okay? So the way we would do that, let's go ahead and write out the function. You can see that we'd have infinity over infinity, which is indeterminate. So let's write it out and see what happens. So we have the limit of x squared minus 4x plus 3 over 2x squared minus 7x minus 4. And we want a constant for where we have the highest power of x on the bottom. So we're going to divide the top and the bottom by x squared. And so that's going to give us, distributing, we'll have 1 minus 4 over x plus 3 over x squared, all over 2 minus 7 over x minus 4 over x squared. And we're taking the limit as x goes to infinity, which means that all of these smaller ratios go to 0 because the denominators are going to infinity. And so as x goes to infinity, this function goes to 1/2. So we get a constant limit again. Let's do the same function and do the limit as x goes to negative infinity. So what I'm going to do now is I'm just, rather than rework the whole problem, I'm just going to change this infinity here to plus or minus infinity, okay? So whether you use positive or negative infinity, you get an indeterminate form. You still do this process, and whether this is positive or negative infinity here, which now it will be, all of these ratios go to 0. We talked about all that before, right over here, right? It doesn't matter if you're dividing by a really big negative or a really big positive, the ratio is going to go to 0. So it actually ends up happening is, as x goes to positive infinity, the y values approach 1/2. And as x goes to negative infinity, the y values go to 1/2. What does that tell us about the graph of this function f? As x goes to negative infinity, as x travels this way, the y values keep getting closer and closer to 1/2. So they might be doing, so let's kind of keep a line where the 1/2 is. They might be doing this thing and getting infinitely close to 1/2, or they might be doing this thing and getting infinitely close to 1/2. We don't know. But as x goes to negative infinity, we definitely know the function keeps getting infinitely close to this imaginary line here, okay? So what do we call this? We've seen these imaginary lines probably in an algebra class. This guy right here gives us a horizontal asymptote, asymptote, at the y value, the line y equals 1/2. In fact, this line comes over here to the right side of the graph too, because as x goes to positive infinity, as x goes to the right, the y values keep getting infinitely close to 1/2 as well. We don't know if they're getting close from the top or the bottom. It can't be both, because then it wouldn't be a function. But it's definitely getting infinitely close to this line. So these limits at infinity can tell you what happens on the extreme left side of a graph or the extreme right side of the graph which is called end behavior. You may have heard that in an algebra class. But now we're seeing it in calculus with limits. All right, so that's fantastic. Let's go back to our function here and see something else. Let's say that we want to, so that's a horizontal asymptote, which can be found by looking at the limits at infinity. Now we could do something like find, so same function, but we could find vertical asymptotes. Well, vertical asymptotes run this way. They are x values. They're at x values on the graph, not at y values like horizontal asymptotes. So if you have a vertical asymptote, that means as you're getting close to it from one side or the other, you're going to go, the y values are going to go to infinity or negative infinity. That happens when you're dividing by 0. So what we could do here is we could rewrite, let me use a different color here. We could rewrite our function. We could factor the denominator. So if we factor this denominator, let's see what we get. We'll have 2x and x. We'll have 4 and 1, and we'll have minus there and plus there, okay? So this function is undefined whenever the denominator is 0. In other words, whenever x equals negative 1/2, we get 0 on the bottom. Or if x equals positive 4, we get 0 on the bottom. So I'm just going to leave this as an exercise to you because this video is not about this sort of thing, but we mentioned asymptotes. So if we talk about horizontal, we might as well mention vertical. So vertical asymptotes might occur whenever the denominator is 0. So what you'd have to do, you'd have to find the limit as x approaches these values, because x can't equal those values. Right, look at the limit of each of these as x goes to negative 1/2 or x goes to 4 of that function. And if you get infinity or negative infinity as an answer, then you know that as you get close to those, your y values are going to go to infinity. Now, you do need to look at both one-sided limits for these, because on one side, your function might go up to infinity, while the other side, it could go down to negative infinity, and that would still be a vertical asymptote on your graph. You don't have to have the same behavior on both sides of the x value.